This presentation is to show how each of the 16 sutras of Vedic mathematics can be used in solving equations. Well, there are many types of equation, as you must know. There are linear types like 2x plus 3 equals 4, easy to solve. Quadratic types where you've got an x squared, there are various types of that too. Cubics, etc., so you've got x to the power 3, 4 and so on. Polynomial equations are included there. Simultaneous equations where you've got two or more equations to solve at the same time. Differential equations, which include dy dx. Trigonometric equations where you've got sin x, cos x and functions like that. Iterative equations where you've got a starting value and a way of generating another value from that, and you repeat the process over and over. And many other types too. For all of these there are special types and there are disguises. So you might get a quadratic equation which has some special characteristic that you can use to solve it very easily. Or it might not look like a quadratic equation, it might be disguised, and you can see through the disguise and solve the equation that way. So for each of these we've got special types, special cases and disguises. Also equations can be merged, equations can be combined together or merged into each other and transformed. So let's go through the sutras, and we'll begin with transpose and apply, because that is the sutra which can be used for solving very simple equations. For example, 2x plus 3 equals 11. Here I'm referencing chapter 11, which is in green, and so it's from Tirjiti's book. So 2x plus 3 equals 11 is an example of a linear equation, and all we do is transpose the signs. So we've got a plus 3 here, which means we subtract 3 from the 11, we transpose, we get 8, and because the 2 is multiplying the x here, we divide that 8 by 2 to get 4. And here's another example. Here we've got the x is multiplied by 3, 1 is subtracted, and we're dividing by 4. So in reverse, we transpose. Because we're dividing by 4, we multiply the right hand side by 4, we get 20. We add the 1, which is 21, and we divide by 3 to get 7. Here the x is repeated. Well, x appears on both sides of the equation, but we can still use the same method. We transpose the minus 6 to the other side, so it gets added to the 14. We transpose the 3x to the other side, so it gets subtracted from the 5x. We get 2x equals 20, so x is 10. Other ways in which we can apply the transpose and apply sutra, Paravartya Yojayet in Sanskrit, are in mergers. That's in chapters 13 and 14 of Tirjiti's book. Simultaneous equations, chapter 15. In the remainder theorem, chapter 9. And it's also in use in transformation of equations. So if you've got an equation and you want another equation which has got the opposite signs to that one, you can apply this sutra there. Or if you want to get reciprocals, if you want to get an equation with reciprocal roots to a given one, you can apply this sutra. That's in Discover Vedic Mathematics book. Now we move on to this sutra, Anarupya Shunyam Anyat. If one is in ratio, the other is 0. Tirjiti gives a nice application of this sutra in the solution of a special type of simultaneous equations. And this is an illustration. We've got a special case here. If you look carefully, you'll see that the ratio of the y coefficients is the same as the ratio on the right hand side. The ratio is 1 to 2. 14 is double 7 and 16 is double 8. And if one is in ratio, the sutra says, the other is 0, which means x is 0. Y is in ratio, so x is 0. And if x is 0, y is 8 over 7. You can see that from here. This can be applied where we've got three variables, x, y and z say, as well. You can see examples in the Discover Vedic Maths book. And here's another nice illustration too. You might notice here in this pair of equations that the 36 is the square of the 6. And the same applies here, that the 4x squared is the square of the 2x. So the same thing applies. We've got the ratio there, and therefore the other is 0, which means y is 0. And if y is 0, x is 3. By addition and by subtraction, sankalana vyavakalanavyam. Here again we can show an illustration from Tirji where we've got special types of simultaneous equations. Here you notice that we've got x plus y and x minus y, and we can eliminate the letters, one of the letters, by either adding or subtracting. So if we add those two equations up, the y's get eliminated because one's plus and one's minus, and we get 2x is 24. So x is 12. If we subtract the equations, the x's get eliminated, and we get 2y is 10. So y is 5. Dhyasati gives an illustration of this in chapter 15. He gives this pair of equations which actually involve the application of this sutra twice. If we've got a pair of equations in which the coefficients have got this particular pattern, the same here, 45 and 45, 23 and 23, and the signs here are both minus and plus here, then by addition and by subtraction we get two equations. By addition we get the first one here. By subtraction we get the second one. If we divide the first one through by 68, we get x minus y equals 3. If we divide the second one there by 22, we get x plus y equals 1. And if we see, we've got a pair of equations similar to what we had up here, and so we can apply the addition and subtraction method a second time. If we add, we get 2x is 4, so x is 2, and then y is minus 1. So that's saving a huge amount of work, because if you imagine solving these by the usual method, it would be a lot of tedious work. But that particular pattern, the special case, means we can apply the sutra and get the answer very easily. If the samachaya is the same, it's 0. Shunyam samya samachaya. Tirji gives a lot of examples of the application of this sutra in solving equations in chapter 12. So, for example, the first illustration he gives is this type of equation where we've got a common factor. The word samachaya has got different meanings, that's why it's left as a Sanskrit term, and one of them is common factor. Here we've got a common factor of x on both sides, and so we can equate that to 0. The common factor is the same, and so it's 0. We get x is 0. And there are many variations of that too. Another class of equations is like this. This would involve quite a lot of work. You'd have to cross-multiply, transpose, cancel, and so on. But here we notice a special characteristic, which is that the sum of the numerators is the same as the sum of the denominators. That is, 8x plus 10 equals 0. The numerators add up to 8x plus 10, so do the denominators, and therefore 8x plus 10 is 0. And the samachaya meaning here is combination or total. The total there is the same as the total there, therefore it equals 0, and therefore x is minus 5 over 4. In fact, there's another solution here, because if we cross-multiply, you see that we get 30x squared this way and 6x squared this way, and the x squared terms don't cancel, so we've got a quadratic and we expect two solutions, and the same sutra gives us the other solution too, simply by subtraction. If we take the 3x plus 4 from the 6x plus 7, we get 3x plus 3, and the same applies over here. The difference is 3x plus 3, and therefore 3x plus 3 is 0, and x is minus 1. And as I showed in a paper from a couple of years ago on Tietge's special cases, this type of equation also applies where we've got trig functions involved and derivatives and so on. Next sutra is specific and general, Vyashti Samashti. Sum and difference of like powers. This is shown in chapter 19, Tietge's book. To take a simpler example, first of all, than the one he shows, if you've got an equation like this, x plus 3 squared plus x plus 5 squared equals 202, we can use the average. And that's what the sutra is referring to here, because using the average involves a specific value taken from a general field. So we're using the average here, and the average of those two terms is x plus 4. So we put a equal to x plus 4, which converts the equation into this one. And the neat thing about this is that because we've got a 1 here and here, these are the same number, then some of the terms cancel out. In this equation, the minus 2a we would get by squaring here cancels with the plus 2a we get here, and so we end up with a very simple quadratic, which is very easy to solve. And once we've got a, of course, we can get x. This is the equation that Tietge uses, so you've got two quartic expressions here, power of 4, and these are added up and equal to 706. So a lot of work is going to be involved. But if you use the average, you can put your a this time equal to x plus 2, and you would find that the odd powers cancel out, and you would be left with a simple quadratic equation to solve. Also, we can apply it in this case here, where we've got cubics, and we can use the average there as well. The ultimate and twice the penultimate. Sopantia dvayamantyam. So here we've got a special type. This is in chapter 16 of his book. You've got this type of equation here. You've got numerators which are the same, and you've got quadratics in the denominators, and those factors have a certain pattern. You've got 2, 3, 2, 4, 2, 5, 3, 4. In this particular case, then we can apply the sutra, and the ultimate and twice the penultimate means the last term, which is the x plus 5, and twice the penultimate, which is twice the x plus 4, equals 0. Then we get this equation, and this complex equation here is reduced to this really simple one just by spotting the fact that it has this special characteristic. The product of the sums, Gunita Samachaya. We can use this in solving polynomial equations. This is in chapters 7 and 9 of his book. So if you had to solve this equation, for example, we see that it's a cubic, and therefore we expect it to factorize into 3 linear factors. And we can begin by finding a linear factor. And in fact, if we put x equal to minus 1 in here, we find it brings the left-hand side to 0, and therefore x plus 1 is a factor. And that x plus 1 must be multiplied by a quadratic if this factorizes at all. So we get something like this, the x plus 1, and there's the quadratic. We know the first and last terms of that quadratic because we've got an x cubed here, so it must be x times x squared. And we've got a 6 here, so it must be 1 times 6. Those are definitely known. What's not known is the coefficient of x. And we can use the sutra for filling in that missing number. The sum of the coefficients here, if you add them up, 1, 6, 11 and 6, comes to 24. The sum of the coefficients here is 2. 1 and 1 is 2. And because this expression is equal to this cubic expression here, then the product of the sums of the coefficients must equal that 24. In other words, the sum of the coefficients here is 2. The sum of the coefficients here is unknown, but the sum of the coefficients here we know is 24. So 2 times something must come to 24. This must be 12. In other words, the sum of the coefficients here must be 12. And because we've got a 1 and a 6, which comes to 7, that leaves a 5 for the missing coefficient. So the product of the sums means the product of the sums of the coefficients. 2 times 12 equals 24. So that gives us the missing 5, and then we can factorize that, and then that gives us the solution to the equation. All the multipliers, Gunaka Samachaya. We can see an application of this in polynomial equations. This is in chapter 9. So taking the same cubic equation as before, if we focus on the 6 here, we can look at its factors. Multipliers, factors and multipliers. Because the factors are 1, 2 and 3, that helps us to factorize the equation and therefore solve it. By the completion or non-completion, Purana Puranabyam. Suppose you've got this equation here, x squared plus 6x equals 16. One way to solve it would be to apply the method of completing the square. This is well known, but it's just got a name here. It comes under the sutra by the completion or non-completion. And so we complete the square. We've got x squared plus 6x, and we know we will get those terms by expanding x plus 3 squared. We get x squared plus 6x. We also get a plus 9, which is cancelled out here. And so we can solve the equation like that. It also can be applied in the case of cubics, and that's what Tirshi does in his book. You can complete the cubic. Also, this sutra can be used in solving differential equations. This is in my book, Discover Vedic Mathematics. Suppose we had a differential equation like this. We notice we've got the sum of products here. And knowing the rule about differentiating a product, we look to see if we can arrange to have a perfect differential on the left-hand side here. I'll illustrate that with this example here, because if we multiply through by x, we get this equation. And then we may notice that if you take the expression x squared y, if you differentiate that using the product rule, you do actually get this. You get the x squared times the differential of y plus the y times the differential of x squared, which we've got here. And so we have arranged for this to be a perfect differential. So the differential of this is equal to 3x squared. We can therefore integrate both sides, get x squared y equals x cubed plus c, and get the answer like that. By one more than the one before, Ikardikena Purvena. Differential equations. This comes up where we're integrating. The power goes up by 1. So if you've got dy dx equals x squared, then y is going to be x cubed over 3 plus a constant. And the power goes up, and so we have one more than the one before. It also comes up in iterative equations, the application of the sutra. This is an example of an iterative equation. We have a starting value called x0, which in this case is 0.1, and that is fed into this equation as x. We work it out, and then that's fed in again and again. That's why it's called an iterative equation. And so that comes under the sutra by one more than the one before, because we repeat the process over and over again. All from 9 and the last from 10. Nikulam Nawatashtara Mandashata. The same iterative equation illustrates the use of this sutra too, because if you take your 0.1 here and put it into there, work that out, you'll get a certain value for x squared over 2, which you then subtract from 1. And in that subtraction, you'll be applying the sutra all from 9 and the last from 10. And when you get your new value and you put it in again, you will be squaring that new value, dividing by 2, and applying the sutra all from 9 over last from 10. In fact, there's a special equation that includes this, 1 minus xi. This is called the logistic equation, and it's very important in population studies. By 1 less than the one before, ekanune na porwena. If we've got x to the 5th, and we differentiate it, we get 5x to the 4th. So we could say, if we've got the integral of y is x to the 5th, then y will be 5x to the 4th. The power goes down by 1 when we do this differentiation. Vertically and crosswise, I can show you an application here in trig equations. Supposing you need to solve tan x equals 6 over 5. That's equivalent to finding the angle here, given these two sides of the right-angled triangle. We're going to do the solution in radians first and then degrees. But what we do is we start off with a known triangle, a known triple. The 3, 4, 5 triangle is known, well known, and it's known to have this angle 0.927 radians approximately in this position. So if this was 3, 4, 5, this would be 0.927 radians. We now put our other triangle, triple, underneath it, so we've got x 5, 6 dash, and we can get the answer to this triple using the known one, using vertically and crosswise. So what we need to do is to make an adjustment to that 0.927 that will give us the value of x. And the adjustment is given by vertically and crosswise. We multiply it crosswise and subtract. So we get 18 take away 20 is minus 2. That gives us the numerator here. And we multiply vertically and add. We get 15 and 24 is 39, which gives us the denominator. And that's easy enough to work out, which gives us our adjustment value and gives us the answer in radians. If you want to do it in degrees, then we would know, presumably, that the 3, 4, 5 triangle has got an angle of 53 degrees, and we're going to compare our triangle with it. So we've got 53 degrees plus a small value to be added or subtracted from it. And what is that? Well, we do the same pattern. We've got 18 minus 20 again is minus 2, and the 39 again from the 15 and the 24. But we have to multiply by this 57, which is an adjustment value that converts radians to degrees. And actually that's quite easy to do, because this fraction is always a small amount. In this case it's about 1 over 20. If we cancel 2 over 40 to 1 over 20, and 20 into 57 is about 3. So we've just got 3 degrees to subtract from that 53, and that gives us the answer 50 degrees. Another way in which we can use this vertical and crosswise sutra, is in solving a certain type of differential equation. Like this, for example, we've got 5y plus 7dy dx equals 10x plus 29. This is detailed in my calculus book. We let y, which is what we're trying to find, equal ax plus b. So we're trying to find a and b. And we begin by taking the coefficients here, 5 and 7. The coefficients of a and b go next, and then the 10, 29 are the coefficients on the right. And we simply apply the vertically and crosswise sutra. So we say the vertical product here has to come to 10, so that tells us that a is 2. And the crosswise total, we multiply crosswise and add, has to come to 29. So here we've got 14, which leaves us 15 out of that 29. So therefore 5 times b is 15 and b is 3. So we get 2 and 3 for a and b, and so y is 2x plus 3. by the deficiency. Well, we can see the application of this in taking square roots. If x squared is 25, we know that x is 5. If x squared is 26, which is 1 more, then x is 5.1. You get 1 more in the tens place. And if x squared is 27, what do we get? 5.2. So it's 2 over 25, it's 5.2. For x squared is 32, that's what, 7 over 25, so we get 5.7. X squared is 33, this is now getting close to the square number 36, and it's actually 3 below 36, so we would need to take 3 off of 6 in the tenths place and get 5.7. Similarly, if we've got x squared is 24, and 24 is 1 below 25, here it was, when it was 1 above 25 we had 5.1, here it's 1 below 25, so we get 5.1, 4.9. And if x squared is 23, it's going to be 2 below, so we get 5.2, which is 4.8. Differential calculus. Here Deirdre uses this, although he doesn't make it explicit. If you're solving the equation x squared equals 11, you use a certain divisor. And that divisor is found by actually differentiating the x squared to get 2x and replacing x with the first digit of the answer. You can see that if x squared is 11, then the square root of 11 is about 3. So we've got our 2x becomes 2 times 3, which is 6. And we use 6 as a divisor. I'm not going to go through this, but there's the 6 used as a divisor, and 11 is the number, and there's the answer down there. And the same thing applies to cubics and higher powers. If you had x cubed is 11, then you would differentiate x cubed to get 3x squared. You would decide the first figure, which in this case would be 2. 2 cubed is 8. And so you would have 3 times 2 squared, which is 12. You would use 12 as a divisor in finding the cube root of 11. So there's the 12. And as I said, this extends to higher powers as well. You can see how this is developed in my book and course, The Crowning Gem. So that's differential calculus, Chalana Kalana Byam. And the last sutra is this one, the remainders by the last digit, Sheshanyankena Charamena. So if we have to solve the equation x squared equals 17, then this would be the beginning of the working. The first figure we know is 4, which is here, and the remainder of 1, because 4 fours are 16, and we've got 17. And as I said before, the divisor that we use throughout is going to be given by the differential of this. So the differential of that's 2x, and twice 4 is 8. We use 8 as a divisor. And the first step after this one is then to divide 8 into 10, which is 1 remainder 2. That goes like that, 1 remainder 2. Now from here on we always subtract the duplex of the figures after the first figure, the 4, from the next remainder. So we will subtract 1 squared from 20, which is 19, and divide 8 into 19, which is 2 remainder 3. Then we subtract the duplex of the 1, 2 from the 30. So the remainders are always reduced by the last digits being the ones after the 4. That's the sutra here, the remainders by the last digit. So subtracting the duplex there, which is 4, from the 30, we get 26, and 8 into 26 is 3 remainder 2. The remainders are reduced by the duplex of the last digits. So that's it, that's the 16 sutras and how they might apply in solving equations.